Hello and welcome to this Python tutorial. I'm super excited because today I'm going to show you a new kind of classifier with new kinds of prediction regions and new kinds of prediction boundary. You're going to see it's quite different from what you've been seeing so far, so I can't wait to show you the final graphic results. Let's go to File Explorer here to set our folder as working directory. So right now I'm going to part 3 classification and decision tree classification. Here we are. Make sure that the social network add CSV file is in the folder, and you can click on this button to set this folder as working directory. Alright, and now let's use our classification template. Let's take everything from here to the bottom, copy, and let's go back here and paste it here. Alright. Let's change the titles of the graph here. Here our classifier is decision tree, as well as here decision tree. All right. And now what we only need to do is to create our classifier here. By the way, decision trees, as you saw with Kirill, are not algorithms based on Euclidean distance. So we would not really need to apply feature scaling here, because feature scaling is, as I explained in the part 1 data preprocessing, is a must-do preprocessing step when your algorithm is based on Euclidean distance. But here, since that's not the case, we would not really need to do this. Besides, when we are making some decision trees model, we want some interpretation, because we can plot some trees to represent all the different conditions in a decision tree. And in the conditions, of course, you don't want to have your scaled value, you want to have the real original value, so you wouldn't apply feature scaling. However, when we plot those prediction regions here, we use a resolution of 0.01. That means that the code here to generate the plots will execute a lot faster if the variables are scaled. So that's a compromise here. We will leave the feature scaling here because we are plotting this plot with the high resolution, but know that if you want to plot some decision trees like the real tree itself, then you can remove this feature scaling part here to have the interpretation of your variables. So here let's keep it this way, and now let's build our classifier. So we're going to import the decision tree classifier class from sklearn.tree, and then we're going to create our classifier object of this class, and then we will fit this object to the training set as usual. So let's first import the class. So it's from sklearn.tree, and then import, and then decision tree classifier. That's your class. That's the class we will use to create our object and fit it to the training set. Then let's create the object classifier equals decision tree classifier, and then let's inspect this class to see what arguments we need to input. So Command I to inspect, and here we go. So parameters. The first parameter is criterion. Okay, so I know it says the default parameter for criterion here is Gini, but we will take the decision trees based on entropy. The most common decision trees are the ones based on entropy. You actually have a lot of amazing classifiers based on entropy, like maximum entropy for NLP. We will see that in the NLP part. So we will get used to this entropy criterion for the information gain. And basically this entropy here is, as it says, a function that measures the quality of a split, so that at the final nodes of your tree, you want each node to be as much homogeneous as possible, that is, with users of the same class. And after each split, the more homogeneous is a group of users, the more the entropy is reduced from the parent node to the group child node. And so after the split, if the entropy in the resulting child node is 0, then that means that this child node is a fully homogeneous group of users, with only users of the same class. And the information gain mentioned here is basically the difference between the entropies before and after the split. So that means that after the split, the higher the information gain is, and the more homogeneous groups there will be after the split. So let's get used to this. Let's get used to this entropy criterion. And so here let's choose criterion equals entropy. All right. Then the next parameters are not very important. So far we only want to focus on building the tree and making some quite good classification. We will see how we can improve the decision tree, and then we will play with those other parameters. But here we will only take the random state parameter just to have the same results, so you can follow the course with me more easily. So random state equals 0. Okay, and now we just need to fit this classifier to our training set. So we use the fit method here, and we apply it to xtrain and ytrain. Alright, and now the whole code is ready. So let's first select this section here that pre-processed the data. Here we go, all pre-processed correctly, perfect. Let's go to Variable Explorer. Everything looks good. Now let's create the classifier by executing this code section here. Alright, all good. You can see that all the parameters that we saw in the class are here the default parameters because we didn't specify them. Now let's do some predictions. Let's apply the classifier to predict new observations, the test set observations. Here we go, ypred, and here is ypred. Let's quickly compare it to ytest just to see how it looks. Okay, wow, this looks very good. As you can see, so far these are correct predictions. Let's look at 10 to 19. Okay, so from 1 to 9 that was perfect, but from 10 to 19 we see some incorrect predictions here. The 13th, the 15th, the 16th, and that's all. Okay, so, but now let's look at how many incorrect predictions we have on the confusion matrix. So let's execute this, and we are ready to find out. So let's take the confusion matrix here, and it looks pretty good. 9 incorrect predictions. Very good, that's an improvement compared to our other models. For example, in logistic regression, I think it was 11 incorrect predictions. And then we had much more incorrect predictions with the SVM. So here it's doing a pretty good job. Okay, and now let's get to the fun and exciting part about visualizing the result. And here it's even more exciting because we are going to get something different. If you followed the intuition course with Kirill, you might guess what kind of prediction boundaries we will get. Try to actually guess what's going to happen. It's a good exercise, good practice. This will allow you to combine your, intuition with practice. So you can pause on the video, you can think about it. Now I'm going to select this, and now showtime. Let's execute this, and here is the decision tree graphic results. Let's enlarge this. Alright, so quite new, right? This is very new. Remember, we either had some straight line when the classifier was linear, or we had some kind of a curve with a lot of irregularities when we used the KNN classifier. We also have some beautiful smooth curve with kernel, SVM, and naive Bayes. But now we have something very different. First of all, the prediction boundary is composed of only horizontal lines and only vertical lines. That's exactly what you saw with Kirill in the intuition tutorial about the intuition of decision trees. You see that it's making some splits based on conditions on the independent variables, which are the age and the estimated salary. So we can clearly see here how it's taking some conditions on some intervals of the variable age. So for example, here it's a condition where the estimated salary is between this value and this value, and the age is between this value and this value. So these are all conditions based on intervals of the independent variables. We can clearly see that here. So that's why the prediction boundary is only composed of horizontal lines and vertical lines. So yeah, that's something pretty new. So wow, so how can I describe this? Well, Well, first of all, we are seeing that it's really trying to catch every single one of user in the right category. Here, as you can see, it doesn't want to miss anyone. Even those red users who were clearly in the green region, like for example this one, well, there clearly was an effort here to catch this red user who is mostly in the green region. However, is there something that is striking your attention and telling you, be careful? Well, yes, we should be careful because this kind of looks like overfitting. Because you see, it's trying to catch every single user into the right category. So I'm not sure that on some new observations, those regions here catch the users the same way with the same, correct predictions. So we'll see that right now on the test set. Let's close this. And let's select this to have a look at the test set. Execute, enlarge, and here is the test set. So actually that's not too bad. But here, for example, this red rectangle here that in the training set was catching some red points because there was red points here in the training set. But we can clearly see that from some new observations, unfortunately here the new observations happen to be green. So that's too bad for this red rectangle that doesn't work for some new observations, especially these ones here. And it's the same, for example, for this rectangle that doesn't catch anything here because there is no new observation point of the test set, no new user of the test set in this red rectangle. So this is absolutely unuseful here. This was just to overfit the training set. So we have to be careful with this, but don't forget at the end of this part is a section about evaluating and improving the classification models. So hold on to that. And by the way, we can still say congrats to this decision tree classifier because it did actually a pretty good job. And by the way, we found 9 incorrect predictions. You can count them and you will count actually 9 red points in the green region plus green points in the red regions. Okay, so I'm curious now to see which classifier you prefer because we are approaching the end of our classification journey. We were actually introduced to a good deal of classifiers. We only have one left. It's the random forest. So you understand that here is one decision tree. So imagine if we do the same classification job with 500 decision trees. Imagine what the result will be. Try to already predict that in your head. You will understand with the intuition section that random forests are based on a majority vote of trees. So since this is one tree, imagine what a team, like an army of decision trees, will do to classify your points. I will let you find out about that. Okay, so that's the end of this tutorial. I was very happy to introduce you to the tree. This is actually a pretty cool model. I like this one very much. And don't forget that decision trees are very good for interpretation because you can build some trees to clearly see the conditions that are making the classification. We will actually plot this tree on R because you'll see that we can do this very quickly in one line and even with 2 words. So we'll do that on R. We won't do it in Python. Here I just wanted to show you the prediction regions, but we'll do it on R. And I can't wait to show you what an army of trees and random forests will do for you in terms of classification. Thank you for watching this tutorial. I look forward to seeing you in the next one. Until then.